Welcome back. Physics builds models. Chemistry builds structures. Biology builds evolutions. 3 ladders, 1 way of thinking. And today, we drop that thinking straight onto a real exam idea, the 2017 VCE Physics Electromagnetic Induction problem set. Today's focus: magnetic flux, Faraday's law, alternators, slip rings, commutators, and EMF waveforms. The graph below shows the change in magnetic flux through a coil of wire as a function of time, t. Which one of the following graphs best represents the induced EMF across the coil of wire as a function of time, t? Step 1. Identify the relationship between magnetic flux and EMF. According to Faraday's law, and incorporating Lenz's law for direction, the induced electromotive force is proportional to the negative rate of change of magnetic flux. Graphically, this means the value of EMF at any point in time is equal to the negative gradient, slope, of the magnetic flux versus time graph. Step 2. Analyze the first section of the magnetic flux versus time graph. Magnetic flux versus time feature: the graph is a straight line sloping upwards. This means it has a constant, positive gradient. Induced EMF: because the gradient of magnetic flux versus time, a constant positive gradient yields a constant, negative value for EMF. Step 3. Analyze the second section of the magnetic flux versus time graph. Magnetic flux versus time feature: the graph is a straight line sloping downwards. This means it has a constant, negative gradient. Induced EMF: a constant negative gradient yields a constant, positive value for epsilon. Conclusion: the resulting magnetic flux versus time graph must be a step function, a horizontal line below the time axis for the first half, jumping immediately to a horizontal line above the time axis for the second half. Correct answer, D. The alternator in Figure 3 has a rectangular coil with sides of 0.30 m times 0.40 m and 10 turns. The coil rotates 4 times a second in a uniform magnetic field. The magnetic flux through the coil in the position shown is 0.20 webers. Calculate the magnitude of the magnetic field. Include an appropriate unit. 3 marks. According to the definition of magnetic flux, the total flux through a surface perpendicular to a uniform magnetic field is the product of the magnetic field strength and the area of the coil. Rearranging this formula, we find that the magnetic field strength is equal to the magnetic flux divided by the area of the coil. Since the coil is rectangular and its length, width, and magnetic flux are known, we first calculate the area of the coil and then divide the magnetic flux by this calculated area. As noted in the examiner's report, the most common error made by students was incorrectly factoring the 10 turns into the flux equation, using phi equals. Students must remember that magnetic flux, phi, is defined per individual loop area, so the total number of loops does not alter the baseline flux calculation for the field itself. Turn count only scales the total flux linkage, used when determining induced EMF via Faraday's law. To find the average induced EMF, epsilon, during a quarter of a turn, we look at how the magnetic flux changes over time as the coil rotates. The alternator starts in a vertical position, where the magnetic flux is at its maximum of 0.20 Webers, and after turning a quarter of a way, it sits parallel to the field lines where the flux drops to 0 Webers. This gives us a total flux change of 0.20 Webers. Next, we determine how long this quarter turn takes. Since the coil rotates 4 times per second, one full rotation takes 0.25 s. A quarter of that time gives a duration of exactly 0.0625 s. Finally, applying Faraday's law for the 10-turn coil, we multiply 10 by the rate of change of magnetic flux to arrive at the final answer of 32 V. VCEE statistical data reveals that this specific calculation proved highly challenging for the cohort, with 54% of students failing to score more than 1 out of the 3 available marks. According to the examiner's feedback, the primary obstacle was not the application of Faraday's law itself, but rather a failure to identify the correct time interval. A significant number of students erroneously substituted either the full rotational period, 0.25 s, or a half-turn period, 0.125 s, into the denominator. This emphasizes the absolute necessity of carefully linking the geometric rotation of the alternator directly to the fractional time interval elapsed. Figure 4 shows the output EMF, epsilon, versus time graph of the alternator for 2 complete cycles. The 2 slip rings in Figure 3 are now replaced with a split ring commutator. On the axis provided below, sketch the EMF, epsilon, versus time graph of this new arrangement for 2 complete cycles. 2 marks. To unpack how this mechanical change alters the electrical output, let's trace the underlying physics using a clear logic ladder. Premise 1. Effect of the commutator. A split ring commutator reverses the connections to the external circuit every half turn of the armature. This changes an alternating current, AC, output into a rectified, unidirectional direct current, DC, output. Premise 2. Waveform inversion. Mechanically, the split ring commutator reflects all negative halves of the original sinusoidal EMF waveform across the time axis into the positive region, or vice versa, depending on initial polarity. Premise 3. Periodicity and amplitude consistency. Because the rotation speed of the coil remains constant, the peak voltage, epsilon, and the total time period, or a complete rotation remain completely unchanged. Conclusion. Action. The resulting graph must display 4 identical positive, or inverted negative, peaks across the 2 duration, dropping to 0 at every 0.5 mark, maintaining the original amplitude epsilon. Electromagnetic induction arises from changes in magnetic flux through a coil. Since flux is defined per loop, the number of turns does not affect the basic flux calculation, it only scales the induced EMF through Faraday's law. The induced EMF depends directly on how quickly the flux changes, so the EMF time graph mirrors the slope of the flux time graph. In the alternator example, the coil's area and measured flux give a magnetic field of about 1.7 T, and the average EMF over a quarter turn follows from the flux change occurring within 0.0625 s at 4 rotations per second. With slip rings, the alternator produces a sinusoidal AC waveform. Replacing them with a split-ring commutator rectifies the output, flipping each negative half-cycle upright, so the waveform becomes pulsating DC, with identical positive peaks repeating every half period. At the end of every lesson, I want to leave you with one idea: learning becomes powerful when you climb the logic ladder. Physics moves from situations to models to equations. Chemistry builds from structure to property to reaction. Biology grows from variation to adaptation to survival. Different subjects, but the same underlying logic. When you learn to decode systems, build ladders, and construct logic, you don't just solve problems, you understand how they fit together. If you'd like to keep climbing this ladder with me, you can find more lessons, breakdowns, and reconstructions on my channel. Thanks for learning with me today.